Let's now do an example of Gaussian elimination with a complex matrix. Okay, so let's keep it simple, a 2 by 2 matrix, but we have, as you can see, some elements that have i's in them, yeah, even in the independent coefficients. So we can still do Gaussian elimination normally in the same way. Okay, so we write the augmented matrix I1 1 minus 2i, then we put a line and we write the independent coefficients. And now we start doing Gaussian elimination. So what are the first non-zero numbers in each row? We have this number and this number. So are there pivots? Well, this cannot be a pivot, because if it's a pivot, it has to be to the right of the pivots above. Therefore, we need this to be a 0. So we are going to use the pivot above, which is an I, to make this number equal to 0. So how do we do it? Always in the same way. The row where we want the 0 to appear, we subtract to it the ratio between the number we want to be 0 and the pivot that we are using to make this number 0. So I, the ratio between those two numbers, 1 and I, times the first row, and we put the result into the second row. Okay? Now, 1 divided by I is equal to minus I. You know that. And therefore, this is equal to R2 plus I times R1. Okay? So doing that, actually I'm going to leave it like that, because it makes sense so that you see that we are just doing the ratio between the two numbers. But remember, this is R2 plus I R1. Yeah? So the first row, we leave it as is. And then we do the first element. We don't even need to calculate it because we know it will be 0. But anyway, 1 plus I times I equals 1 minus 1 equals 0. So we are okay. And then this second element is minus 2I plus I times 1, which is the first row. So that's equal to minus 2I plus I equals minus I. And then never forget, this is a common mistake, never forget to also do the operation on the independent coefficients. Yeah. So 0 plus I times I, which is 0, 1, that's 0 minus 1, that's minus 1. So we arrived here. Excellent. Now, what are the first non-zero numbers in each row? So the first row we have this one, and the second row we have this one. So these are now our pivots, and we are in row echelon form. We can do the staircase. So we are in row echelon form. So now we can solve for x. Yes? So what is the case out of the three cases? In which case are we? Case 1, unique solution when all the columns have pivot. That's the case we are in. We had 2 columns and we had 2 pivots. Yeah? So every column has a pivot. This means that there is a unique solution. Okay? So the original matrix A had a determinant that was not equal to 0. It had an inverse. We could find the solution if we wanted by doing inverse of A times vector B. Or we can find the solution by inverse substitution. So we're in case 1, unique solution, and we are going to use inverse substitution. So starting in equation 2, so starting in row 2, we have that minus I x2 equals minus 1. Therefore, let me write here row 2. Therefore, ix2 equals 1. So x2 is 1 over I, which is minus I. So that's the first variable. And now we go upwards into row 1. So row 1 is telling us that I times x1 plus 1 times x2, which is minus I, equals I. So if we put the minus I on the other side, we have that I x1 equals 2I. Therefore, x1 equals 2. Right? Therefore, if we write those as a vector, that is equal to 2 minus I. and this is a single vector, which is a solution to the system. Okay? If we had calculated the inverse and then multiplied times b, we would have gotten the same result for vector x. Thanks for watching.